A beverage can looks simple until we ask the question what it takes to make one. Then it becomes a fascinating metallurgy problem. In my research, I deal with recycled aluminum alloys for beverage cans and what it takes to make one. So, for beverage cans, the aluminum alloys have to be strong, light, formable, easy to manufacture in large quantities, and nowadays, increasingly circular. Imagine that you are in industry and then the beverage cans that you recycle in your supermarkets come back to the melt shop. In industry, we melt those beverage cans, we cast big ingots, and then those ingots are heat treated. After heat treatment, they are hot rolled, cold rolled, and then they are shipped to the can maker. What we are doing in my PhD is trying to simulate exactly that. So we are tackling this issue both experimentally, but most importantly, computationally. And what we are striving to do is to build a through-process framework that understands the underlying process structure property linkages. We are interested in how compositional variability affects microstructure of recycled aluminum alloys during processing. Therefore, more specifically, we are interested in what we call texture, which then affects those properties. Texture means that the crystals inside the metal orient themselves in particular directions during processing, and this orientation that they have affect the properties we mentioned before. More importantly, how we shape a texture also affects what we call anisotropy, and then the properties we mentioned before change with respect to direction. Our computational approach lies in what we call integrated computational materials engineering, or in short, ICME. So, since we're dealing with multiple steps along the process chain, we need different tools to tackle this issue. So, we combine thermodynamics, mechanics, and microstructural evolution simulations. In the thermodynamics front, we used cathode-based tools for the casting and homogenization stages, and then for the thermomechanical part, we are using different kinds of software for mechanics and deformation, and then microstructural evolution. On the mechanics front, we are using our own in-house developed code DAMASK, where we are simulating the deformation processes and how each grain deforms inside the metal and how texture is formed, using full-field crystal plasticity simulations. Then, after that, we couple it with the recrystallization software we are developing here to model how recrystallization textures arise from the DAMASK input. After finishing with my university and military obligations back home, I joined industrial R&D with the prospect of doing a PhD there. But unfortunately, it did not materialize. I did not lose sight of my goal, though, and I tried to find the right institution to do it. At the time, reaching out to my supervisors here felt like a far-fetched thing to do, but I did. And here I am now at MPI, having found my Ithaca. In my case, it's my father. My father, he is a mechanical engineer, and for the past 26 years, he has been working as a production engineer in a cold rolling aluminum plant. So, yeah, I think it's natural that he is my role model. My advice to the youngest scientist would be work hard, get your fundamentals right, and dream big. To me, building a career in science is just like building a pyramid. If your foundation is weak, then you cannot rise very high. Therefore, I would advise you to get your fundamentals right, work hard, be curious, be passionate for what you are doing, and always when you are working and striving towards a goal, be consistent and disciplined. And one more thing, don't be afraid to try. I tried, and here I am now.